The morning of November 24, 1950, arrived cold and clear across the Appalachian foothills. Temperatures held in the low 30s. The air carried the dry edge of late autumn, the kind that made breath visible and turned grass brittle underfoot. Smoke rose vertically from chimneys in small towns scattered through the valleys of eastern Ohio, western Pennsylvania, and the highlands of West Virginia. The stillness was ordinary for the season. Trains moved slowly through the narrow river valleys, following routes carved by water over millennia. The Norfolk and Western, the Baltimore and Ohio, the Pennsylvania Railroad, all maintained their schedules, hauling coal and freight through passages where ridgelands rose steeply on either side. The geography was unforgiving in its verticality. Narrow valleys separated by parallel ridges running northeast to southwest, each ridge blocking wind and trapping weather in predictable patterns. In communities like Elkins, West Virginia, and Uniontown, Pennsylvania, the rhythm of the holiday weekend proceeded without interruption. Markets closed early. Families gathered in homes heated by coal stoves and wood furnaces. The infrastructure of daily life, power lines strung along wooden poles, water pumped from wells or municipal systems, roads maintained by county crews with limited equipment, functioned as it always had. The region's isolation was geographic and cultural, shaped by terrain that made travel difficult and communities self-reliant by necessity. The Thanksgiving weekend was a pause in the industrial calendar. Steel mills in Pittsburgh and Youngstown ran skeleton crews. Coal mines in the southern West Virginia coalfields observed the holiday, though some maintenance shifts continued. Small towns in the mountains remained quiet, their populations accustomed to winters that brought cold and snow, but rarely disruption on a scale that exceeded local capacity to respond. By late afternoon on the 24th, the temperature had begun a slow descent. The National Weather Bureau station in Pittsburgh recorded readings in the upper 20s. Wind remained light. Barometric pressure showed no unusual decline. Weather observers noted the approach of a cold front from the northwest, typical for the season, expected to bring clearing skies and colder temperatures through the weekend. No advisories suggested anything beyond routine winter conditions. The landscape itself, steep ridges covered in bare hardwood forests, valleys threaded with creeks and small rivers, communities connected by two-lane roads and single-track rail lines, remained as it had been for generations. The mountains absorbed the cold without comment. Wood smoke continued to rise. Trains moved through the gaps. The ordinary architecture of life in the Appalachians held steady, built on assumptions about winter's predictability that had been reliable for as long as anyone could remember. A low-pressure system formed over the Great Lakes on November 23, 1950, moving eastward at a moderate pace. The cyclone deepened rapidly as it crossed Lake Erie, its central pressure falling to 979 millibars by the morning of November 25. This was unusually low for a continental system. The pressure gradient, the rate at which atmospheric pressure changed over distance, tightened sharply, creating conditions for sustained high winds across a broad region. The Appalachian mountain range, running from Georgia to Maine, acts as a barrier to westerly airflow. When strong winds encounter these ridges, they accelerate through gaps and valleys in a process known as channeling. Wind speeds at valley floors can exceed those at ridge tops by significant margins. The topography also traps cold air in hollows and basins, creating temperature inversions where warming air aloft prevents mixing, keeping surface air well below freezing for extended periods. Infrastructure in the region reflected the technology and economics of the mid-20th century. Power lines ran overhead on wooden poles, exposed to wind and ice. Homes were heated primarily by coal or wood, with little insulation by modern standards. Water systems relied on exposed pipes vulnerable to freezing. Road maintenance equipment consisted of plows and sand trucks, adequate for typical snowfalls, but limited in capacity for heavy accumulation or prolonged operations. The region's economy depended on transportation networks, rail lines for coal, highways for goods, that had minimal redundancy. On November 24, the Weather Bureau issued cold wave warnings for the Ohio Valley and Mid-Atlantic states. These advisories predicted temperatures dropping into the teens and single digits, with strong northwest winds following the passage of the cold front. Wind advisories noted the potential for gusts exceeding 50 miles per hour in exposed areas. Snow was forecast for higher elevations, with accumulations expected to remain light to moderate. The warnings were routine, distributed by teletype to regional offices and broadcast on radio stations. No indication suggested a departure from manageable winter weather. The vulnerability of the region was structural and cumulative. Power distribution networks were radial, with generation plants feeding into transmission lines that branched into progressively smaller distribution lines. A single failure point, a downed line, a damaged substation, could cascade into widespread outages. Communication systems depended on telephone lines that shared poles with electrical infrastructure. Transportation arteries followed valleys, meaning that a single blockage on a mountain pass could isolate entire communities. The redundancy necessary to withstand simultaneous failures across multiple systems did not exist. The pressure readings from November 24 showed an accelerating decline across the region. Pittsburgh recorded 998 millibars at noon, dropping to 984 millibars by midnight. The gradient between the storm center and the high-pressure system building behind it steepened. Wind speeds increased proportionally. The combination of low pressure, steep gradients, and favorable topography created conditions for extreme wind events. The forecasting tools of the era, surface observations, upper air soundings, and synoptic charts, captured the pattern but underestimated its intensity. The temperature at Pittsburgh dropped from 32 degrees Fahrenheit at midnight on November 25 to 18 degrees by 6 a.m. The decline continued through the morning, reaching 11 degrees by noon. Wind speeds, measured at the airport on relatively flat terrain, increased from 15 miles per hour to sustained winds of 40 miles per hour, with gusts recorded at 68 miles per hour. In the mountains, where topography amplified airflow, wind speeds exceeded these measurements significantly. The collision between Arctic air pushing south and residual moisture from the Atlantic created heavy snowfall across the higher elevations. Snowfall rates reached 2 to 3 inches per hour in the Alleghenies. The wind picked up the falling and fallen snow, creating whiteout conditions where visibility dropped to zero. Drifts formed rapidly, accumulating to depths of 10, 15, 20 feet in areas where wind patterns concentrated the snow. Roads disappeared under uniform white surfaces. Landmarks became indistinguishable. Observers at weather stations documented the progression. At Elkins, West Virginia, the anemometer recorded sustained winds of 56 miles per hour before the instrument failed. At Morgantown, gusts reached 82 miles per hour. At higher elevations, where direct measurements were unavailable, the evidence appeared in the physical damage. Trees snapped at mid-trunk, metal roofing torn from buildings, power poles toppled in sequential rows along ridgelines. The wind produced a continuous roar, a sound that penetrated walls and made conversation difficult even indoors. Power lines began failing in the early morning hours of November 25. The combination of wind stress and ice accumulation, freezing rain had preceded the snow in some areas, exceeded the structural capacity of wooden poles and the tensile strength of copper wire. When one line failed, the load redistributed to adjacent sections, creating cascading failures along entire circuits. By midday, communities across eastern Ohio, western Pennsylvania, and northern West Virginia reported complete loss of electrical service. Transportation systems ceased functioning. The Pennsylvania Turnpike, opened only a decade earlier as a modern highway designed for year-round operation, became impassable as drifts buried the roadway under snow measured in feet rather than inches. Railway lines froze as switches jammed with snow and ice. trains attempting to maintain schedules stalled in drifts, their locomotives unable to generate sufficient traction to continue. The Baltimore and Ohio reported multiple trains stranded between stations, their crews and passengers waiting in unheated cars as wind rocked the carriages on their tracks. Communication failures compounded the isolation. Telephone lines failed alongside power lines, cutting contact between communities and regional centers. Radio stations went off the air as their power supplies failed or their transmission towers sustained damage. The Weather Bureau station in Pittsburgh continued transmitting observations via backup systems, but the information reached a shrinking audience as receiving equipment lost power across the region. The physical motion of the storm, wind-driven snow moving horizontally, temperature continuing to fall, pressure systems churning overhead, created an environment where human activity became impossible. Visibility remained at near zero. The cold penetrated buildings, overwhelming heating systems designed for typical winter temperatures. The disorientation was mechanical, landmarks erased, sounds distorted by wind, spatial relationships rendered meaningless by uniform whiteness. By evening on November 25, the storm had established itself across the Appalachian region. Snowfall continued through the night. Wind speeds remained high. The temperature held in the single digits. The infrastructure of modern life, power, transportation, communication, had ceased to function across an area covering tens of thousands of square miles. The electrical grid across Ohio, Pennsylvania, and West Virginia experienced cascading failures throughout November 25 and 26. Major generating stations remained operational, but the distribution network, tens of thousands of miles of transmission and distribution lines, sustained damage at thousands of individual points. Power companies reported that between 40 and 60% of their service territories lost electrical service. In rural and mountainous areas, the percentage reached 90% or higher. Restoration would require not just reconnection but physical reconstruction of damaged infrastructure. Highway systems became impassable. State highway departments in Ohio, Pennsylvania, and West Virginia reported that virtually all roads in the affected region were blocked by drifting snow. Measurements of drift depth exceeded 20 feet on exposed stretches of highway. The Pennsylvania Turnpike remained closed for multiple days. Secondary roads, many of them unpaved or minimally maintained, disappeared entirely. Snowplows operated when possible, but many became stuck in drifts or suffered mechanical failures in the extreme cold. The equipment available, mostly single-axle trucks with front-mounted blades, lacked the capacity to move the volume of snow deposited by the storm. Rail transportation, the primary means of moving coal and freight through the mountains, stopped. The Norfolk and Western Railway reported more than 100 trains stalled on its lines in West Virginia. The Baltimore and Ohio faced similar disruptions across its network in Maryland, Pennsylvania, and Ohio. Snow packed into rail switches, preventing their operation. Ice formed on rails, reducing traction to near zero. Multiple locomotives froze, their water systems rupturing as temperatures remained in the single digits for days. Passengers and crews in stranded trains endured hours or days without heat, as coal supplies for onboard heating systems ran out or could not be accessed. Bridges across the region accumulated ice at a rate that exceeded design tolerances. The weight of ice, combined with wind loading, stressed structural members beyond their capacity. Several bridges sustained damage. Some collapsed. The Wheeling Suspension Bridge, spanning the Ohio River, was closed after inspectors observed dangerous deflection in the deck caused by ice accumulation and wind force. Smaller bridges on rural routes failed outright, their wooden or early steel structures unable to withstand the combined stresses. Water systems froze in communities across the affected area. Distribution pipes, many of them laid in shallow trenches or running through unheated spaces, solidified as temperatures dropped below zero and remained there. Wells froze at the surface. Municipal water treatment plants lost power, shutting down pumping operations. Even where water remained available, the means to distribute it had failed. Fire protection became a critical concern, though the cold reduced the risk of structural fires spreading rapidly. Coal deliveries, essential for both industrial operations and home heating, ceased as transportation networks failed. Steel mills in Pittsburgh and Youngstown, dependent on continuous deliveries of coal and iron ore, faced inventory shortages that threatened production shutdowns. Homeowners relying on coal for heat found their supplies dwindling, with no means of resupply. The industrial economy of the region, built on the extraction and processing of coal, confronted the irony of being unable to move its primary product during a period of acute need for heating fuel. Buildings across the region sustained structural damage. Flat-roofed commercial and industrial structures collapsed under snow loads that exceeded engineering assumptions. The weight of accumulated snow, measured in tons on larger buildings, caused progressive failures of roof trusses, leading to complete collapses in some cases. Residential structures with steeper roofs generally survived, though many sustained damage to porches, additions, and outbuildings. The cold wave that accompanied the storm persisted. Temperatures in the Appalachian highlands remained below zero for 3 consecutive nights. Daytime highs failed to reach double digits. The combination of low temperature and high wind created conditions where exposed skin could freeze in minutes. The mechanical systems of the era, furnaces, water heaters, vehicles, were not designed for prolonged operation in such extreme cold. Failures compounded, each one creating new vulnerabilities in systems that had already been stressed beyond their capacity. Road clearing operations began on November 27 as wind speeds diminished and snowfall tapered off. State and county crews worked systematically to reopen primary highways, using every available piece of equipment. Progress was measured in miles per day. Secondary roads remained impassable for weeks. The Pennsylvania Turnpike reopened to limited traffic on November 29, having been closed for 4 days. Rural communities in the mountains remained cut off from outside contact for periods ranging from several days to more than a week. Reaching isolated mountain towns required coordination between multiple agencies and the use of specialized equipment. In some cases, residents walked out along trails or logging roads to reach communities where roads had been cleared. Supplies reached cutoff areas via airdrops organized by the National Guard and Civil Air Patrol. The U.S. Army deployed vehicles and personnel to assist with snow removal and delivery of emergency supplies, particularly fuel and medical supplies. The cold wave extended through early December. Temperatures remained below normal across the region for 2 weeks following the storm. Rivers froze, some of them solid enough to walk across, an unusual occurrence for rivers as large as the Monongahela and the Kanawha. The landscape took on a uniformly frozen appearance, rivers locked in ice, fields buried under snow that resisted melting, forests silent and still. The documented casualties from the storm totaled 353 deaths across the affected states. Causes included hypothermia, carbon monoxide poisoning from improper heating methods, heart attacks during snow removal, and traffic accidents. Economic losses were estimated at multiple hundreds of millions of dollars, accounting for infrastructure damage, lost industrial production, agricultural losses, and emergency response costs. The steel industry alone reported production losses exceeding $50 million due to transportation disruptions and power outages. The storm's impact on weather forecasting and infrastructure planning was immediate and sustained. The Weather Bureau initiated a review of its forecasting procedures and communication protocols, recognizing that the intensity and impacts of the storm had been underestimated. This review contributed to the eventual establishment of more sophisticated forecasting systems and more aggressive warning protocols for severe winter weather. The experience demonstrated the need for better understanding of how topography influences local weather conditions, particularly wind speed and snow accumulation. Infrastructure improvements followed over subsequent years. Power companies reinforced transmission systems and increased investment in redundant distribution networks. State highway departments expanded their equipment inventories and developed protocols for rapid mobilization during major snow events. Building codes in some jurisdictions were revised to increase snow load requirements, though implementation was gradual and not uniform across the region. The physical evidence of the storm persisted in the landscape. Abandoned vehicles remained buried in drifts through the winter, excavated only when spring thaw made recovery possible. Mill towns that had lost power and water supply for extended periods faced population decline, as residents questioned the viability of living in locations so vulnerable to isolation. The storm marked a threshold in the region's relationship with winter weather, a recognition that the mountains could impose conditions that exceeded the capacity of existing systems to protect and sustain the communities built within them. The silence that followed the storm was profound. The usual sounds of industrial activity, trains moving through valleys, mills operating, traffic on highways, had ceased entirely. The quiet persisted for days in some areas, broken only by the wind and the occasional sound of equipment working to clear roads. It was the silence of a system that had stopped, a mechanical pause imposed by forces that had not been adequately anticipated or prepared for. The storm had demonstrated the region's vulnerability not through any single catastrophic event, but through the simultaneous failure of multiple interdependent systems, each one essential to the functioning of modern life in the Appalachian highlands.